Chapter 5, Carbon. In this chapter, we will look into a branch of chemistry called organic chemistry. Organic chemistry studies the structure, properties, and the reactions of organic compounds, which contain carbon-carbon covalent bonds. Why is carbon special? Let's begin by looking at its atomic size. In the graph below, we made a plot of atomic size versus the atomic number of all elements in the carbon family. As you can see, all elements, including silicon, germanium, tin, and lead, fit well into a linear line. But carbon is an outlier. Its atomic size is significantly smaller than the rest of the elements in the same family. Atoms of an element are extra small when they have only a few electrons, and those electrons are held closely to the nucleus, which is the case for atoms across the very top of the periodic table in period 2. For atoms further down in the group, there are additional electron layers further from the nucleus, and those outer electrons feel less pull from the positive charge of the nucleus. Therefore, those atoms are larger. We refer this phenomenon as the uniqueness principle. The small size of carbon lets it get very close to other atoms. We learned from the last chapter that carbon atoms have 4 valence electrons. There are 4 vacancies in their Lewis structure to be filled to achieve an octet. Therefore, carbon atoms make 4 bonds. Methane, Ch04, is a simple carbon-containing molecule. Let's take a look at the structure. In picture A, we have a Lewis dot structure of methane. Imagine the dots around the carbon atom are coming from the valence electrons of the carbon atom. The little x are coming from the valence electrons of hydrogen atoms. By sharing these electrons, each hydrogen has access to 2 electrons. Recall that hydrogen is from the first period of the periodic table. It can only hold 2 electrons. This is the duet rule. So all hydrogen atoms are happy now. Carbon has access to 8 electrons. It has achieved an octet. So the carbon atom is happy. Picture B here is the molecular structure of methane. A line like this represents 1 bond, which is equivalent to 2 electrons. In picture C, the 4 hydrogen atoms make a tetrahedral shape around the central atom. The 2 hydrogen, these 2, are on the line, are on the same plane as the carbon atom. The hydrogen atom on the wedge, this is the one on the wedge, is pointing towards you, the viewer. The hydrogen atom on the dashed line, this one is on the dashed line, is pointing away from the viewer, going behind the paper. All bonds in a tetrahedral structure make a 109.5 degree angle to each adjacent bond. This drawing does not correctly show the structure of methane in 3-dimensional. Diamonds are formed from a strong 3-dimensional network of covalently bonded carbons. All carbon atoms are tetrahedrally bonded to one another. Diamond is the hardest natural substance known. Each covalently bonded carbon in a diamond bonds to 4 other carbon atoms around it. The central carbon shares 4 electrons with 4 adjacent neighboring carbon atoms to achieve a stable octet. Because of that, diamond is resistant to chemical reactions. Other than single bonds, carbon can form multiple bonds to other atoms. A double bond is formed by sharing 4 electrons between 2 atoms. In the structure of ethylene below, the 2 carbon atoms are sharing 4 electrons. each carbon atom contributing 2 electrons towards the double bond. In addition, it also bonds with 2 hydrogen atoms. There are 8 electrons around each carbon atom. The octet rule is satisfied. Each hydrogen atom obeys the duet rule, and all atoms are happy in the entire structure. Carbon can form a triple bond with other atoms. A triple bond is formed by sharing 6 electrons between 2 atoms. Acetylene is the simplest molecule containing a triple bond. The 2 carbon atoms of acetylene are sharing 6 electrons, each carbon atom contributing 3 electrons towards the triple bond. In addition, it also bonds with 1 other hydrogen atom. There are 8 electrons around each carbon atom, and the octet rule is satisfied. Each hydrogen atom obeys the duet rule, and all atoms are happy now in the structure. An allotrope is a different form of a pure element. Other than diamond, elemental carbon can form graphite, graphene, and buckyballs. They are all allotropes of carbon. Graphene is a single atomic layered honeycombed carbon shown in picture A below. It is another allotrope of carbon. It is the strongest material known. When multiple layers of graphene are stacked together, graphite is formed. Humans have known graphite for a long time. It is the lead used in pencil in our everyday life. Although it is called lead, it is not made of elemental lead from the periodic table. It's actually graphite. A pencil mark on paper contains thousands, if not hundreds, of graphene layers. Take a guess at how scientists separate a single atomic layer graphene from graphite before flipping to the next slide. By tape, a Scotch tape. In the year of 2004, 2 British chemists used Scotch tape to strip off a single atomic layer graphene off the graphite. Later in 2010, they were awarded the 2010 Nobel Prize in Physics for groundbreaking experiments regarding the 2-dimensional material graphene. Graphene is only made of carbon atoms. It conducts electric current at amazing speed. Graphite, or the pencil lead, consists of layers of graphene as shown in picture B here. It is greasy, slippery, and black in color. All bonds in graphene are in the same plane. However, the bonds between the planes are held together by the weak van der Waals forces. That's why we can easily slice off graphene from graphite layer by layer. If the layers are held by covalent bonds, it would be impossible. Another allotrope of carbon is Buckyball. It gets its name from Buckminster Fuller, who patented the geodesic dome. The Buckyballs have the shape of a soccer ball. Every pentagon is surrounded by 5 hexagons to form a spherical shape. Single, double, and triple bonds have different lengths and strengths. Bond energy is a measure of bond strength of a chemical bond. It is the amount of energy needed to break the atoms involved in a molecular bond into free atoms. Triple bond has the strongest bond energy, or to say, it requires the greatest energy to break a triple bond between atoms. The next is the double bond, followed by a single bond. In an analogy, think about the level of strength needed to break a single wooden stick versus 2 wooden sticks versus 3 wooden sticks. You would require to put in much more strength to break 3 sticks than a single stick. The more bonds between atoms, the higher the bond energy. On the other hand, bond length is defined as the distance between the centers of 2 covalently bonded atoms. The higher the number of bonds between atoms, the stronger the pull between the 2 atoms, and the shorter the bond length. A single bond has the longest bond length, followed by a double bond. Lastly, the triple bond. The nature of bonds between atoms determines the substance characteristics. Hydrocarbons contain only carbon and hydrogen atoms. They form the framework of most organic molecules. Common elements of organic molecules each form a known number of bonds. For example, carbon forms 4 bonds, hydrogen forms 1 bond, oxygen and sulfur each form 2 bonds, nitrogen forms 3 bonds. The oxygen, sulfur, nitrogen, and any halogens are called heteroatoms. They are atoms other than hydrogen that attach to the hydrocarbon skeleton. Different notations are used to represent organic molecules. In this picture, we have hexane molecule. On the very top, we have the full structure of hexane, or sometimes called a complete structure. The middle one is the line structure, or called a bond line structure. The last one is the ball stick model of a molecule. In a full structure, all atoms and bonds are clearly drawn out as in this example. Hydrogens are single bonded to the adjacent atom, and all carbons are making 4 bonds to the adjacent atoms, and all bonds are clearly drawn out. Let's take a look at the line structure of hexane given in the middle of the picture. Notice how much easier it would be to draw the line structure rather than the full structure. The line structure for hexane is 5 short lines connected in a zigzag pattern. The end of each of those lines represents 1 carbon atom. Hydrogen atoms are not shown at all, therefore we must imagine where the hydrogen atoms would be filled in. The numbers shown in the figure count out the carbon atoms in the molecule. Beginning with the leftmost end, we can count 1 through 6 carbon atoms. Note the end of the line structure are counted as carbon atoms. Take a look at this is carbon number 1 at the end of the line that matches the full structure carbon number 1, the terminal carbon. And then this is carbon number 2, matches the carbon number 2 of the full structure. And 3, 4, 5, and 6. The ball and the stick model shows the 3D arrangement of atoms in the molecule. The white color ball in here represents the hydrogen, and then the gray color ball, slightly larger, represents the carbon atom. Many organic molecules contain a special kind of ring, called a bending ring, that's drawn in a distinctive way. The bending ring is a ring of 6 carbon atoms. The bonds between these atoms alternate around the ring. First, a single bond, then a double bond, then a single, a double, a single, and a double. The full structure of bending ring is given in picture A. The line structure of bending is given in picture B. The lengths of all 6 bonds in the ring of bending are actually between a double and a single bond, more like a bond and a half. Because the bonds are all the same length, the line structure can also be drawn as a hexagon with a circle inside, as shown in picture C. The fever relief drug acetaminophen, aka Tylenol, contains a bending ring, is shown in picture D. Organic molecules are incredibly diverse. There are literally millions of non-organic molecules, and tens of thousands of different organic molecules exist in the human body alone. Why is there such incredible diversity among them? It is because carbon atoms can make chains, and those chains can be branched or can make rings of various sizes. The picture on the right shows all of the ways you can connect 6 carbon atoms using only single bonds. The figure shows that there are 15 ways to arrange 6 carbon atoms without a ring or with only a single ring. There are more than 100 ways to arrange 10 carbon atoms connected by a single bond. Heteroatoms appear in organic molecules in a particular groupings that are found again and again in nature. We refer to these common groupings of heteroatoms as functional group. There are too many functional groups to cover all of them, so we have selected just a few important ones as examples. A sulfide functional group contains sulfur atom. They're usually stinky and smelly. Example structures are shown in here. Next is a carboxylic acid functional group. They usually have the structure of COOH. Carbon is bonded to a single oxygen, then bonded to a double bonded oxygen, circled in the middle molecule. It's part of important building blocks of biological molecules, such as amino acids. Amine functional group contains a nitrogen atom, are commonly found in amino acids as well as drugs, circled here in this molecule. Question 1. Which atom has the smallest atomic size? A. Arsenic. B. Antimony. C. Phosphorus. D. Nitrogen. Please pause your video here. The correct answer is D. Nitrogen. All 4 atoms are from the same group, with nitrogen being the smallest. According to the uniqueness principle, elements from period 2 are extra small because they have only a few electrons, and those electrons are held close to the nucleus. As a general rule of thumb, atomic size increases as we move down the group. Question 2. What is the bond angle in a molecule with a tetrahedron shape? A. 120 degrees. B. 109.5 degrees. C. 107 degrees. D. 104.5 degrees. Please pause your video here. The correct answer is B. 109.5 degrees. Please refer to slide number 5 for explanation. Question number 3. What is an extended system of repeating covalent bonds? A. Network solid. B. Covalent solid. C. Tetrahedron bond. D. Multiple bond. Please pause your video here. The correct answer is A. Network solid. A solid like a diamond that has an extended system of repeating covalent bonds is a network solid by definition. Question number 4. How many double bonds are in this molecule? A. 3. B. 4. C. 5. D. 6. Please pause your video here. The correct answer is C. 5. By looking at the structure to your right, double bond looks like a little equal sign between atoms. So there are 5 of them. 1, 2, 3, 4, and 5. Question number 5. Select the statement that is true about carbon-carbon bonds. A. The bond length is the longest in single bonds, and the bond energy is the highest in triple bonds. B. The bond length is the shortest in single bonds, and the bond energy is the lowest in triple bonds. C. The bond length is the longest in single bonds, and the bond energy is the lowest in triple bond. D. The bond length is the shortest in single bond, and the bond energy is the highest in triple bonds. Please pause your video here. The correct answer is A. The bond length is the longest in single bonds, and the bond energy is the highest in triple bonds. Refer back to slide number 15 for the orders. Question number 6. What is an allotrope of carbon? A. Water. B. Carbon dioxide. C. Ozone. D. Diamond. Please pause your video here. The correct answer is D. Diamond. we refer to different forms of a pure element as an allotrope. So only choice D, diamond, is made of carbon, the element, and everything else are compounds. Question 7. This functional group is used to make complex biological molecules. It contains one carbon atom, two oxygen atoms, and one hydrogen atom. Choice A, amine. B, carboxylic acid. C, sulfide. D, alcohol. Please pause your answer here. The correct answer is B, carboxylic acid. Let's take a look at each of the wrong answers to find out why. According to the question, the functional group contains carbon, oxygen, and hydrogen. Amine is a nitrogen-containing atom. It usually has a NH2 attached. Choice C, sulfide. Sulfide is a sulfur-containing molecule, with sulfur being in the middle, so this one's wrong. And then lastly is an alcohol. Alcohol usually have a OH in their structure. So D is out. The only correct answer is carboxylic acid, which is COOH. Question 8. What is the chemical formula of ethyl methyl ketone? A, C4H8O. B, C4H6O. C, C5H7O. D, C5H6O. Please pause your video here. The correct answer is A, C4H8O. To answer this question, you simply count the number of different atoms in this molecule. So we're first going to begin with carbon. I'm going to write the symbol C for carbon. They are 1, 2, 3, 4 of them. So I'm putting 4 as the subscripts. Next, I'm just going to use a green color for hydrogen. Let's count the number of hydrogens. 1, 2, 3, 4, 5, 6, 7, and 8. So 8 is the subscript of hydrogen. Lastly is oxygen. Oxygen, I'm just going to use a black color. And then there's really just one oxygen right here. So we're going to put 1 for the subscripts. But remember, 1 as a subscript can often omit it. Therefore, that gave you the correct formula as C4H8O. Question 9. What is the tube-shaped molecule with the same type of carbon framework that makes up the Buckyball? A, nanoball. B, Buckytube. C, nanotube. D, Buckminster fullerene. Please pause your video here. The correct answer is C, nanotube. Refer to the picture number 4 to your right is a nanotube. Question number 10. How many bonds does nitrogen form? A, 4. B, 2. C, 1. D, 3. Please pause your video here. The correct answer is D, 3. Hydrogen atoms form 3 bonds. If you look at the picture to your right, here is bond number 1, bond number 2, and bond number 3. If you look at the other nitrogen, same thing holds true. Bond number 1, bond number 2, and bond number 3. Hydrogen makes 3 bonds.